From Platteville with MTM, Metals Minor, so same program you guys are in.
Andy Buckner, graduated same program in December of '08, so a few years ago now.
Oh, I guess my position at Signicast is I'm a project engineer.
I'm a process engineer.
We'll start out with a little bit of the history of Signicast, for those of you who didn't come on the tour the other day or don't know anything about us yet. Started out as Sinai Cast. We made boat transom signs. So any plaques you see on ships from back in the 50s, 60s era, that would be something that would be our initial market. New ownership opened up 1981, and that's kind of when we transitioned into, we were at the Brown Deer facility, we transitioned into many other markets. 1990, we were landlocked at the Brown Deer location, so we opened up a plant in Hartford, which is Module 1, you'll see in the bottom right corner. We'll touch base on that in a little bit. We're considered one of the largest commercial investment casting companies in the world. Our funding and backing comes from the Pritzker Group since 2008. So they allow us to do any improvements needed and kind of give us a nice long leash to keep the leading edge in the industry. This is our location in Brown Deer. 98,500 square feet. That's where we're maxed out at. This plant is nice because it has so much manual operations. We can do a lot of R&D testing, a lot of flexibility in our process. So we pour many of our more exotic alloys there. We have manual operations in our dipping, pouring, all those areas, so we can get more eyes on the parts where it is pretty critical.
Laser pointer.
Okay. Because of the manual operations in the plant, we're allowed more flexibility with high and low volume and part sizes. We can go up to 100-pound pour weights in a lot of applications. So that's where you'll see like larger pumps, pump housings and all that. We're also able to do a lot of prototyping because it may be more of a one-off thing. Is your hand up back there?
Yeah. When you say air pump for weights, what kind of material? Like, are you talking about aluminum or is it?
We're able to pour a lot of the ferrous alloys, as well as we do pour aluminum in Brown Deer. We can get into the alloys in a little bit, but to give you an idea, all low carbon steels. We do 300 and 400 series stainless, as well as a few like tool steels and
Nickel-based alloys, cobalt-based alloys.
a lot of the more exotic ones are in our Brown Deer facility.
Yeah. The vast majority of what we pour is carbon and stainless steel. The Brown Deer facility is about 75 to 85% stainless steel.
One other benefit to our Brown Deer facility we'll touch on in a little bit is soluble and ceramic cores. We'll go further in depth in case you don't know about that, but that is one major thing. Oh, there we go. Here's our Hartford facility. We now have 7 modules. Each building is considered a module. So we kind of go around the loop there. That's module 1. We jump across to 2, and 3 and 4, and up on the hill is 6 and 7. That's the.
Aren't you guys building another one after that too, or no?
Area.
Yep.
6 is here, 7 is here, and then we so we started out with this here, and we ran out of space. So we bought the 52 acres behind us, which is this area up here where 6 and 7 is, and then we also have room for 8, 9, and 10.
So right now we have.
Is that across the road?
Nope, it's all connected.
It's up to that back road.
It's
there.
up to the back road. I'm short, so I can't reach it even with the pointer. But
Longer pointer.
all the way up to this road. So that gives us enough space for 10 vehicles that back 52 acres is actually about 20 feet higher in elevation. So we have an elevator here and a skywalk that goes all the way across to get to those upper two modules.
So on these grounds, we have 5 casting modules. They're like individual foundries, essentially. We can all work together, but each one has their own teams that can support themselves. So there's five modules that cast parts. We have 1 module that does solely machining and assembly operations. And then our module 6 will be our main shipping module, as well as more assembly and post-cast operations that may not necessarily be machining
And heat treat.
and heat treatment.
You want to tell them like what each module is staffed with, engineer-wise?
What's that?
Engineer-wise, what each module has?
Oh, sure. Well, we can get into it right here. With each module, because it's set up as its own foundry, we have a staff, a salaried staff, which will consist of at least 2 to 4 project engineers. We have a process engineer dedicated to that module, and then we have our supervisor for the plant, and I think it's about 10 to 12 people that actually are out on the floor.
Depending on the plant, yeah.
Yes, some of them have more automation, which is able to replace a human body, but for the most part, there's not many people for the amount of product flow we have. There's a lot of automation that assists us, and you'll see that throughout the rest of this presentation.
Mods 1 and 2, which were our 2 initial plants in Hartford, have about 25 to 30 production employees in each plant. And modules 3 and 4 run on about 12 production employees. So just from our automation, we reduced our workforce to about 12 people.
So you can see the 435,000 square feet is significantly larger than our Brown Deer facility, so we can handle a lot more volume of parts through all this area. And so now this is more of our medium to high volume production, and when I say that, I mean medium would be in, we'll call it like the 10 to 20,000 pieces per year, where a customer may order that quantity in a year, up to, we have jobs that run several hundreds of thousands. Commonly we consider high volume anything over about 60 to 70,000 pieces in a year. What else does he have now?
A stick There we go.
Capabilities of each individual module are individual heat treats. So that's more of your basic normalized heat treatments, which would homogenize the microstructure, give you a better ability to machine the parts, as well as make them more consistent microstructure throughout. We also have a few extra processes such as straightening or blasting operations that we're able to do per module. But if it gets into anything significant, we go into module 5, which is our machining and assembly plant. We also have a powder coating operation. So we like to cover a lot of things in-house, and if it does get more exotic than that, we have a pretty good supplier base, which allows us to subcontract parts out, and we can still be a one-stop shop for our customer, which really helps out in the market. This is some of our customer base. Granted, we have many, many more, but these are most of the popular ones. I think our top 3 are Harley-Davidson, Emerson Group, and John Deere, and Caterpillar is a close 4th. And I mean, we branch from everything from the gun markets to the oil industry to agricultural, heavy machinery, a little bit of everything. Electric, as you see with S&C Electric. The only things we don't really get into is Tier 1 automotive, anything that flies, such as like aerospace items.
Anything that leaves the ground and has to come back intact.
We may do small things that go in planes, such as like handles or trinkets in the cabin, but nothing in the engine. And what was the last one? Anything that goes in the body, medical items. Quality, we have a very stout quality system set up that each new part project has to get proven through dimensional studies as well as NDT, which would consist of X-ray and magnetic particle inspection. And so now you're proving out your process to your customer, and that documentation gets sent to them. We can get into that later, but it's just a little tidbit, and we are ISO and TS certified as well, which is doesn't mean a lot in this case, but when you get out into the industry, that's a huge deal for our customers. So now we're going to get a little bit more into what is the investment casting process. And have you guys talked about this at all yet, like the fundamentals of investment casting?
I can't remember, I had 2 different classes. Have I?
Yeah.
All right.
I knew you guys were coming, so.
Knew we read.
Okay, you had to read about it a little bit?
Yeah.
Okay.
You're supposed to.
Good. All right. Well, so some of this might be a little more specific to Signicast, but as an industry-wide, this will be the fundamentals. And if you have questions, raise your hand. That's fine. So what we do is we build an injection die out of aluminum. Just your standard 70-75 aluminum in a T6 condition. Yeah, what we advertise is that we'll build the tool for the life of the project. It'll maintain its structure. Because wax is not an abrasive material, that allows us, we put wear pads on any movable components, and we maintain our tool at our cost, which is usually fairly minimal. We range anything from a manual tool, which would consist of just an open close with a human actually opening the 2 die halves, to semi-automatic and automatic tools, which we'll see in a little bit here. But this is just one example of this is more of a simple injection die. You can see in the back corner, that's a slide. So in this case, this is a frame joint for Harley-Davidson, which you'd have tubes that slip into here. And we have this slide come in so it will fill in a blind pocket. So there's many ways. Once you start looking at a part, you gotta determine the parting line. And for a toolable case, you may have to do movable components in order to fill that feature out. So now this is an example of a semi-automatic die. This is in one of our Module 3 or Module 4 wax areas.
That's the part popping up and out.
Right, so you see your tool is right there. This robot has suction cups on it, so it has a vacuum system. It's going to reach in, and the suction cups will activate, which will grab the pattern out. It just dropped it in a water bath. The water bath allows it to fully solidify, so it's more of a easily handleable part. There's also a nozzle on the robot that has a mold release agent to it. So we're able to spray, which lubricates the mold as well as allows the pattern to be removed.
Does it spray the mold release like right after it picks it up, or does it put the part down in the bath? And
It will put the part down. There's not necessarily a time limitation for this. It's a silicone agent that it acts as a lubricant essentially. In a lot of cases, like you guys are probably more familiar with sand casting just due to the general nature of the class. But advantages of investment casting you'll see in a lot of our tools is we don't have major draft angles. Our parting lines are in many cases not even identifiable when you look at the wax pattern. That was kind of a quick video, but you can go back again. This is an automatic press. So the difference here is this is opening in a vertical orientation and the part just drops out and it's dropping into a water bath. So you don't have to have a robot or an operator there continuously maintaining the die. There will be a robotic arm that comes down and sprays it in a set period of time, which we have determined, our wax techs determined. And other than that, it's just going to pump out as many patterns as you set it to.
How do you figure out when to automate it fully versus semi-automatic or manual?
A lot of the determination comes from the size of the pattern. So we have some patterns that may be something like the size of, these are little jaws for a needle nose, like multi-tool. A lot of these would run in our smaller part plants, so modules 1 and 2. Characteristically, they run small parts. So little stuff like this is an assembly, but these would be individual, so we'd pump out a bunch of these. And they're able to fall into the water bath without getting damaged or running into each other. And they cool fairly quickly. In the case of the larger parts, if they fell into a water bath, they could get damaged or they could hit each other. Also, they have to have more care for the duration of solidification in the wax itself. So we have to be a little more delicate with larger parts.
And complexity of the parts. In a semi-auto press, we can have parts that are a lot more complicated. We can have more slides in multiple directions.
Right.
In an automatic press, we can usually handle 1 or 2 slides, typically in 90-degree orientations from each other, but that's about tops that you can do. So anything more complex than that, we'll go semi-auto with it.
At this stage, we have an operator that will be assembling the parts onto a common sprue. Now I know you guys know what a sprue looks like. I saw them hanging in the shop there. So we have a catalog of different sprues that are modular to our process. So yeah, she is pretty quick. A lot of our wax techs are from experience. They get pretty well trained.
This is the University of Police Department. A severe thunderstorm warning has been issued for Grant County until 7:15 p.m. The storm should reach Platteville at around 7:45 p.m. This warning is for southern Grant County, and the wind gust, we're expecting wind gusts up to 60 miles per hour, torrential rains, and dime-sized hail. Again, this is the University of Police Department. The severest thunderstorm warning is expected until 7:15 p.m. The storm should reach Platteville at around 6:45 p.m. This warning is for southern Grant County, and we are expecting wind gusts of 60 miles per hour, torrential rains, and dime-sized hail. Please watch your local weather for more information.
Right now it's sitting in the middle of the pack parking lot. But I'd rather in a little more sheltered spot.
It's a square body Chevy.
Yeah? What do you think?
I'm not even needing ID. I'll claim insurance.
Alright, so this stage of the process is a little more specific to Signicast. We hang our molds onto what we consider a cluster hanger. This allows us to process several molds at a time. So these will be all the same part number. We'll show that again. They're all the same part that are on there. We can usually hang 3 to 5 molds on one hanger. And this is just getting entered into our, we consider it an ASRS, but it's automatic storage and retrieval system. It's essentially a robotic crane that picks and places different items.
Apparently you don't, Gary, no.
This is where Andy can explain a little more.
So from here, we take that cluster that we just assembled in wax, and we dip it in our ceramic slurry, and then coat it in a stucco. So we have multiple slurries that we can use, starting with a very fine slurry with fine particles in it to coat the detail of the part and give us a nice surface finish on the wax. And then, so this would be a prime slurry. We're going to drain it off to get a nice even coating of slurry on the mold, and then go into the sander and coat it with stucco. So just like the slurry, it's a real fine slurry. We also use a real fine stucco on the prime dips, which is the early on dips. later on, we'll start using a coarser stucco and a slurry that's made more to build bulk on the mold. So we put between 5 and 10 dips on our wax patterns. Gives us a shell that's about 3/8 of an inch thick, give or take. Between every dip, we dry the mold for between 1 to 3 hours. It's pretty typical before we put the next layer on.
So, Andy, maybe explain some characteristics of what would the consistency of a prime dip versus a backup dip be, like Zahn Cup reading wise?
Okay, sure.
Not details, but I guess like feel, you know.
Right, your prime dips have a higher zircon content, so they tend to be a lot heavier. We also run them at a thicker viscosity. So Zahn 5 Cup, which you guys will see here in a little bit, will run about a 48 to 50 second viscosity in prime slurry. And then on our backups, we run it a little thinner so that it flows around, but it also doesn't drip as much as our prime slurry. So we can run it thinner, it flows into cracks and crevices, but then it kind of hangs on to the mold. So our backup slurries will run in the 24-second viscosity range. So it actually does, it's physically thinner, but it builds bulk a lot faster, just from the materials that are in it, that are composed of it.
And then with the sands, we have 3 primary sands.
We use 3 different types of stucco. We use a zircon stucco for first dip, which is real fine and it's very non-reactive. So when the metal flows in against it, the metal doesn't react with the stucco or the prime slurry. From there we'll go on second dip and sometimes third dip. We'll use what we call an S1 stucco. It's slightly coarser and it's a fused silica material. Because it's not in direct contact with the metal, we don't need the inertness that we do with the zircon and prime. And then for our backup dips, we go to an S2 stucco, which is even coarser yet. Also a fused silica material, and that's just to build strength and bulk.
And now to compare that to what you guys will actually be doing in class here, we'll have some sort of a hybrid mix of slurry that will help you guys set up. Andy will work through the details of that a little later. Your initial stuccos will be a zircon, and then your backups, which we're going to get some sand over here, so your backup stucco will be an S2. Because you're not in a production atmosphere, you don't need to build as robust of a shell. That would be, you know, as handleable, I guess I'd say, as we need to. So a
Yeah.
zircon and an S2 would be sufficient.
Would be sufficient, yeah. We'll kind of, because you guys don't have as much equipment, you can't really run multiple slurries, multiple stuccos all at the same time. So we'll give you a slurry that's kind of good for all the dips. May not be the best for all the dips, but it'll work for all the dips, and it'll allow you to build a decent shell.
What's in the S2 again, did you say?
S2 is a fused silica material. It's just a much larger grain. So after we build our shell and it's dry, we go through and we have to remove that wax from the shell, obviously. We use a steam autoclave. So we'll take the molds, put them in an autoclave that pressurizes the molds to 150 psi and then heats the molds to about 350 degrees. And that all happens within 3 seconds. So as you can see, we push the cart in the autoclave. He's going to close the door, and as soon as he closes the door, a big steam valve opens, steam rushes in, and that's where we get that high pressure and high temperature almost instantly, like I said, within about 3 seconds. So what that does is hold pressure on the outside of the shell, keep it from cracking, and then the heat melts the wax off the bottom. So after that, we have all of the bulk of the wax out of the mold. We then run it into a burnout oven. The burnout oven is 1800 degrees. We burn out our molds for about 4 hours. And what that does is burn out any residual wax. That burns out any residual wax that's left in the shell, and it sinters the ceramics to make it strong. So we use a pusher type system burnout oven, so when we pull one mold out of the front to pour it, another one gets pushed in from the back, and it's like a conveyor line that goes all the way through. So this is the other end of the burnout oven. The mold coming out, we have, in mods 3 and 4, we have a robot that goes in, grabs the mold. It's going to pull it out of the oven, flip it over, set it in a sandbox, and another robot is going to come over and fill it with metal then.
Approximately how long has it been from the initial dipping to this point before it gets filled?
It's from when it starts dipping or when it ends dipping. When it ends dipping to this point, you're talking about 5 hours.
Okay.
We usually can build a shell in about 24 hours.
Okay.
So then after the mold is filled with metal, we take a cover and put it over the mold. There is, you can see down here, you got some fire action going on in there. We actually take a scoop of sawdust and put it in the sandbox. Then we set that hot mold in there, gets filled with metal. Just the heat ignites the sawdust, starts consuming oxygen. Then we put a can cover over the top. It burns up all the oxygen inside that can. So the metal inside the mold can't oxidize as it cools.
If you worry about oxidation, is that, like, how permeable is that shell?
The shell is actually quite permeable. If you take just we do a test, it's called a permeability test, where we'll actually take a ping pong ball, build a shell around it, then burn the ping pong ball out and see how much nitrogen we can flow through to test permeability. But we only use 1 psi of nitrogen, and it flows through at something like 24 cubic centimeters a minute, something like that. You can take that, we take a tube and stick it in the ping pong ball, but you can actually blow on it, and you can blow air through the shell. It's more permeable than you think, actually. It's kind of surprising. So, because if you think about it, you got your mold, you have metal coming in, that metal chokes off the neck of the mold almost instantly. So you have that whole mold that's full of air at that point. That air has to go somewhere. A little bit will come back up through the sprue and kind of gurgle, but the vast majority of it has to go out through the shell. So we rely on permeability to really aid that. So if you have a shell that is not permeable enough, you'll end up getting air that gets trapped in the outsides of those parts, and you'll have non-filler gas. A little moist out there? So after the metal cools, we go to shell removal, and what we'll do is put our mold in a water blast cabinet.
We need one of those water blast cabinets, by the way.
Oh, okay, yeah, we'll put that on your wish list, okay. And we use high pressure water to remove the shell. So it's a pressure washer on steroids. We run about 10,000 psi.
Do you reclaim any of that stuff though that you use at all? Or not the stuff, but the sand anyway?
The shell that we blast off,
None 100%.
not 100%. We as a company don't do much with it, but we do have other companies that buy it from us and use it for different things. We have one company in particular that buys some material, grinds it up, and actually uses it for cores for green sand casting. So they'll grind it up, use a little sodium silicate, mix it together.
And nice refractory, core.
Yeah, exactly. It works out really well for them. It's also used quite a bit for roadbed material, just for fill. So we keep dabbling in different things that we can do with it, and we haven't really come up with a good one yet. So there's lots of good material there. It's just processing it in a way that we can use it again. So trying to adapt it to our process. So we'll play this one more time if you guys didn't see it. You can see how quickly the shell really comes off. It's kind of hard to see if you look through the... And the molds come out with little to no shell left on them after that.
Do they go in there hot?
No, well, hot is a relative term. Usually
Depends how fast
we
we
water
push them through.
blast 250 degrees or less. So they're still pretty warm, but not,
Not warping warm.
yeah, exactly.
Start putting cold water on hot castings and they start to warp.
Especially 400 series stainless and some of your higher carbon steels have a tendency to crack.
If it was still that high, you could heat treat it too, couldn't you? Not at 200 degrees, obviously, but if it was still really hot.
Not in
No.
a controlled enough fashion.
Yeah.
Yes,
You're
technically
spraying
you
it
could.
on one little spot.
Yeah, you're only spraying it with, like a pinpoint water, so it's, yes, you probably could, but
The
it's,
surface area isn't enough to try to heat treat it.
yeah, exactly. And to be able to control it that way would be almost impossible.
Because this is module 3 and 4.
Yeah, so, no, we would do cold breaker. So from there, we go to our finishing department. Yeah, probably. We go to our finishing department where we will grind the gates off of parts, if that's what's required from our customers. We'll also do a shot blast, clean up the outsides of the parts. From there, we'll do a final inspection, as well as any gauging that's required. And that all comes down to the customer and what's the requirement for that particular part. That's a part-by-part type of situation. So do you want me to
Yep,
keep
I
going?
can.
Doesn't matter to me.
So at this point, it comes to our inspection booth. So we'll have operators that 100% visually inspect these parts. Now, every part gets visually inspected. Some parts require an attribute inspection as well. So attribute gauging would be the application for this. And what we mean by that is if you have, say for instance, these through holes, if they have to be consistently in line, as well as a certain size, we have calibrated gauge pins that will drop through at the minimum diameter and the maximum diameter. And that will help us identify where we fall in tolerance. That's our quick checks we do on the floor. We don't do any SPC data collection, which would mean that you actually calculate a variable reading. So we don't calculate what the actual size of that hole would be in production and where it falls in the tolerance, just that it passes or fails. Post-cast operations we'll perform is heat treatment, straightening, machining, plating, painting, assembly. All these we kind of touched on before, but again, this is a lot of the things that we can do in-house. It branches beyond that outside our facility. So now we'll get into the design stage of it. Now this is what will directly pertain to you guys, and not only your project, but also if you get into the investment casting industry. So Andy, if you want to talk about the
Yeah, we can
alloys
do
and
this.
stuff.
Typical alloys that are investment cast would be your plain and low alloy carbon steels. So your 1018, 1020, 4130, 4140, 8620, those type of alloys. Your 300 series stainless. Now, a lot of you are probably familiar with 304 stainless, 316 stainless. Once you get into cast alloys, the nomenclature changes a little bit, so we deal with CF alloys, CF3, CF8, and the M versions of those as well. We also do 400 series, lends itself very well to investment casting. So your 17.4s, your 15.5s, CB30s. Tool steels, A2, D2, S7, those types. Nickel-based alloys, so your CW2M, as well as some other various cobalt alloys, which usually work pretty well.
Now, these are all fairly exotic compared to what you guys are doing in the foundry, but real quick, count who's doing what for alloys. Do you have any decisions yet? Is it primarily? Yep.
Yeah, for your casting.
17.4.
Okay. 17.4.
Really?
Why did
Is
you pick
anybody doing
17.4?
something?
That's
That's a good question.
Why would you use 17.4? Just out of
Just
curiosity.
be interesting, have stainless steel.
Sure.
Okay. Are you familiar with any of the properties of it, or?
I know that it's really hard, and before heat treating it, I can drill and tap it, and then I'll heat treat it.
Ideally, you'd like to anneal it before that, so that puts it into a softened state, so you don't hit any hard spots
Okay.
throughout the microstructure of the part.
Solution anneal it would be the way to go for starters.
But then there are hardenable heat treatments that you could do to that. So that, I don't, it'd be,
Machine's a lot easier.
Being a,
yeah,
yeah,
you really would want to normal, or do an anneal to it if you want to machine it. Anybody else? What are you guys doing? Not sure yet.
we'll find out.
Slackers. Not sure yet, you're supposed to have it done for today.
I mean, I'm all good. It's on my sheet.
How about somebody in the back? What are you guys doing for an alloy for your project?
We're getting some
Anybody?
bronze, if you
Show
want to do
'em
a copper base, we're gonna do 875.
Okay. Any aluminum?
Yeah, there's some aluminum.
Peter, you're doing aluminum, right? Just kind of
A356 or what?
just probably.
Probably 356.
Yeah.
Airplane's back, by the way.
Yeah.
No, yeah, I told him.
Okay.
Okay, sounds good. Aluminum is one that we're getting bigger and bigger into recently. Within the last year, we've started pouring aluminum regularly. We have a couple production parts in aluminum now. So that's kind of new for us. We're still learning as far as aluminum goes. Yeah. Okay, so different structures when you're comparing casting to wrought alloys. Wrought or in a wrought alloy, typically you have bigger, should I say this? You have better properties, it's directional. You have better properties in one direction compared to another. Whereas a cast structure, you tend to have pretty uniform properties all the way around. Now, obviously, depending on the geometry of your part, that's going to change a little bit. But typically speaking, you get a more uniform structure, metallurgical structure and properties. So you can see this microstructure here is more uniform. You can see some of your ferrite, you have grain boundaries here, more uniform throughout. Where you have in your wrought, you can see all this ferrite that you have here, and you have more bands. So this is going to give you decent mechanical properties this way, but it's not going to be very good this way. So that's where casting kind of has an advantage. Now, sometimes you want more in one direction than another, and that's where choosing your process really comes into play.
Well, the forging would be a connecting rod for car. You'd have good mechanical properties, very good mechanical properties in one direction.
So, heat treatments that can be performed on investment castings, and here basically the sky is the limit, but some of the common ones, solution anneals, more common in your stainless steel, anneal, isothermal anneals, spheroidized anneals, normalized, quench and temper. We won't go through all these, but some of the ones you're going to see more commonly are your solution anneals, a normalize, and a quench and temper. Those are your main ones. Those are the ones that we deal with mainly. We'll do some carburizing where we want to put more carbon on the surface of the part. We do this a lot in like an 8620 type of alloy where we have a relatively low carbon content in the part, so that gives us good ductility and toughness, but then we want the case to be hard, so we'll carburize the outside layer to make the outside real hard, but still give us the ductility and toughness of the inside of the part. So that gives you a real hard, tough part.
Have you guys studied heat treatments at all? You got to that at all?
A little bit in the intro, but yeah, metallurgy we do. So 8620, a lot of alloying elements, 0.2% carbon, right? So it doesn't really harden that much. A lot of gun parts are made of 8620, right? It's a
Yes.
case hard on the outside. So
It
you do wear
Depends on
resistance,
the
but
part,
it's tough.
yeah.
8620 and 1025 is another common one, but that percentage area of carbon.
Then we get into some of our more exotic heat treats that a lot of these we don't do at Signacast, but we'll send it out to an outside heat treater to do for us. Nitriding, carbon nitriding, ostempering.
What's this melaniting and nitronic?
Melanite?
Yeah.
Melanite is a process that it basically, it's a heat treat that brings it basically develops a white layer on the surface.
Melanite on the surface.
Which now it has anti-corrosion properties
It's really
as
big
well
in
as,
It's-
what's that?
It's really big in gun parts.
It's
Yeah.
similar to
You'll
nitriding.
You'll see it's a black surface finish.
But it's like parkerizing or something like that? Or
Similar to parkerizing, but
This
More
also is,
chemistry in it.
it provides a case harden also.
Yep.
Very thin, about 2 to 5/10 of a thousandth. Yeah,
Oh.
very thin.
And then
Nitrotech, I think, is kind of a specialty.
Kind of like a coined phrase.
Right, exactly, kind of like Kleenex,
Trademark phrase,
so to
yeah.
speak, trademark phrase. Similar to nitriding, but I believe it goes deeper into the surface, creates a thicker layer,
Because
tougher
nitride
layer.
is usually really shallow also.
Nitriding is usually only like 3/10 or something thick. So,
Many cases for like the nitride, the nitrotech, are if the customer wants a surface that appears black in color, it's a characteristic of the heat treat process. And if they want some wear resistance, so a lot of user interface on machine items, like lawnmower components and whatnot that are more industrial, where you're adjusting the height of the mower, all those teeth and everything, that they don't necessarily need something as drastic as case harden, but they want the teeth and everything to keep the shape for a duration of time. This would be the process because it's a very thin, hard surface.
so any questions on heat treating?
Those just go in a big container, like racks, or they individually heat
We
treated?
heat
or-
treat, depends on the part, but usually we put our parts in a heat treat basket, which is about 4 feet by 6 feet by about 8 inches tall. And we'll stack 4 of those baskets together to make one heat treat load.
But they're like individually, like,
Depends on the part. Some we just dump in the basket, kind of even them out. Some will actually put rods in between and stand up each part
Right.
individually.
some you got custom baskets, right?
All the
Some,
baskets are
all the
pretty much
baskets
the
are
same.
pretty much the same. If something requires kind of a goofy custom thing, we'll send it out to an outside heat treater. We do have some of our bigger parts that are 100+ pounds. We send out, and that they can do like 6 parts at a time. Costs us an arm and a leg to heat treat them, but it's easier than us doing it in-house. So.
Okay.
Sorry
So
about the
the-
DD&T.
yeah, this is something, I don't know that you guys touch too much on dimensional aspects of your parts. Something that drives the industry. So if you don't make a part to tolerance, the customer doesn't care what it looks like or how great it looks. It has to fill their application. So we'll cover some, just these are a reference point for tolerances in the investment casting industry. There's many exceptions and gray areas to this, but a rule of thumb, anything up to a 1/2 inch is plus or minus 7/1000ths. So 7/1000ths, think of, Kyle always says a hair. So one hair is, it's 3/1000ths thick.
3 to 4.
So
Blonde hair's a little thinner.
So, a couple of hairs, think of that as, that's 1/2 of your tolerance there. So we're talking pretty tight. Some smaller parts, I mean, something like the thickness of this, we could hold a very tight tolerance on. Plus or minus 7 is industry-wide, that's your universal, what we would recommend the customer puts on a print. If they have something more what they consider a special characteristic, we can hold plus or minus 3, 4 right in that range, and that's in thousandths. So,
Consistent.
yes, consistently. And the rule of thumb is it goes up 3 thousandths per inch. So as you can see on this scale, it's, anything over or up to an inch is 10 thousandths plus or minus. So again, you can tweak depending on what the application is. In a lot of cases, if it's a very tight tolerance the customer requires because of their overall design and assembly, they require a certain hole or a certain linear dimension to hold. We may have to run a sample and see where we're at. Once you get a sampling of parts, you can perform a dimensional study. Capability studies start at 30 pieces, and that will give you an idea of what you're statistically capable of in your process. From there, we can tune in the dimensions of our wax tooling, which is the aluminum tool. We can adjust those sizes of the part, and we can tune this thing right to where the print needs to be. In cases where maybe you have a long, flat part, and you can't hold an overall flatness on it or an overall parallelism across the two faces, well, we have operations like straightening. We can also gauge the parts to see where they're at, and we can even machine them in our Module 5. So all these you can start thinking about when you look at a print from a customer and you see these dimensions and whatnot. You need to be able to identify, okay, this is going to be something critical. We may have to do a post-cast process in order to tweak that dimension in. The better you are at identifying that up front, the easier your job is and the happier your customer is as well. So we're going to get into some different characteristical concepts. So for this is basically identifying a little more into the GD&T range of things, but if you think about, I don't know how familiar everybody is with datum structures and GD&T, but
You guys
basically,
know what GD&T is? Geometric dimensioning and tolerancing. You should know, at least if like an employer asks you what that is, you should at least know what the hell those letters
Yes.
mean.
it is very beneficial. So
Geometric
Well-
dimensioning and tolerancing.
we'll breeze across this, but your datum structures are where your locating points are on this part. So datum A would be if you put that one face up against a wall and just held it right there. Now that part is locked, it can't go up and down, for instance. So that's datum A. And then you'd slide it up against another wall, that's datum B. So now the part is locked in, and you're going to check the position of a hole in reference to those two datums. So you're bringing your measurements off those side faces to that hole position. So this gets you thinking of how different characteristics of the part could give you different readings on your hole locations and your datum structures as well.
So the datums typically are where you set up your part in the fixture to be machined.
Right.
Otherwise, it's going to be very hard to hold tolerances if you're machining it off of a surface that's not a datum. What is its relationship to the actual datum, right? So, so typically it's 3 points in the bottom,
Yes.
2 on one side, and then there should be 1 in the back or something like that. Would be a datum C.
Right.
3 points of contact at all times. So datum C would be the back face.
Yeah, back face, yeah.
So position of two holes to one another. So if you're thinking about a shaft with two different diameters on it, well, if you're going to machine this on a, say you machine it on a lathe, well, you can assume that your two diameters are going to be concentric to each other. So that means that when you look at it from the end, the smaller hole is perfectly in the middle of the larger hole. In the casting process, that's not always the case. Due to process variation, say the part may droop a little bit, your holes may be slightly off. So we talk about position of the holes. And now there's a formula in this case. It's the tolerance that you should be applying to that is the diameter of the first hole, the first boss, minus the diameter of the second boss, times 5/1000ths of an inch. That should be what your rule of thumb tolerance should be. So if you're ever looking at a print and you see that, you should request that, see why they have it so tight, or if it's wide open, then, it gives you an idea of, okay, that's not very critical to the customer's application.
So, that's 5,000 inch, that's your tolerance, that's pretty big.
Well, it would be, so if this is 1, if the larger one is 1 and the smaller one's a half, that's a half times 5 thousandths. That's the way you'd run the formula. So, but in certain cases, say this is a dowel pin that's going to locate 2 parts together. So if this fits in one hole, and then the next part is going to line up on that top dowel, they're going to want that to be in a correct position. If it's not, your customer has big issues. Circularity. So now, again, with like a machining process, you're assuming it's perfectly round. In casting, you're always going to get a little variation, so we like to have a tolerance that allows this variation in a certain amount. For this instance, this is a guard for push buttons on a machine. So, not necessarily critical, but if it's above what you would see by the naked eye, then it just looks bad for the quality of the part, right? So, but if this was more critical, you'd see a tighter tolerance on that. Profile, this can be across many different applications, but that's getting a little more deep into GD&T.
It's something, you guys, while you're here, we don't teach as much as we should. It's something that you should, we're working on that, but it's something that you should kind of strive to learn about. If you go to work for Point Precision or something like that, I know that they have a training program there specifically for geometric dimensioning and tolerancing.
Yeah, we do too, we send all the engineers through it.
Yeah.
And you'd be surprised at how much you know and how much you don't know.
Right.
Once you go through the class, because a lot of it seems pretty straightforward, you're like, oh yeah, I got that. But then when you actually start looking at it more in depth, there is way more to it than what meets the eye.
And when you actually start looking at, it's all nice to do the stuff on the book and everything, but then you get a print in front of you, you're like, okay. And plus you're trying to correct the mistakes that the engineer made on their tolerances, so
Well, and you'll find a lot of times that the customer puts some ridiculous tolerances
That's what I
on
mean,
it
yeah.
because they think tighter is better. So they'll put plus or minus 5 on everything and they think it's good. When you look at it from a functionality standpoint and there's no reason most of those tolerances should be as tight as they are. And they don't realize that tighter tolerances equals more expensive, generally speaking.
This gets into more of like aspects of flatness and straightness. So like I mentioned with straightening or machining a certain face, if it's critical, then we would probably have to do one of those processes like a coining or a flattening of the part or a machining of the face. But general casting tolerance allows you 5 thousandths times the overall length. So if you have a long flat surface, you can ideally, if the print was designed correctly and it allots for it with the part application, you should get a pretty good tolerance for that part to have sort of a bow to it or some sort of a sink. And that's just, it's all variables of the casting process once again. Perpendicularity, angularity, parallelism, these are all common things once again. So in this case, if you have an assembly that say this part has to be perfectly flat, this is your datum A face, so that's the most critical face in this case. That would be the locating flat face, and then they're looking for the perpendicularity of this wall. Now say if you extruded those lines out way far, if you put plates across both of those, and that's not perfectly 90 degrees for perpendicularity or within the tolerance, you could be messing up the application of the part or whatever remaining components are. So what we like to do is always see what the application is, see how we can help, see what the tolerance stack up is of the rest of the parts. Wall thickness, and this is kind of all over the board depending on part feature, but we have stuff down to, what is it?
About 20 or 25 thousandths wall thickness. That's really pushing the envelope. That's not in a vacuum or rollover.
Right.
We can just naturally cast it.
But industry standard is 90 thousandths is a typical thin wall, and it of course gets thicker from there.
And it all depends on the length too. I mean, you could fill out a very narrow section if you only got to go 1/4 of an inch. But if you're trying to fill out
Right.
something that's
Whole surface.
6 inches long
Right.
at only 30 thou thick, that's going to be a whole lot tougher.
Now these next two slides you really gotta pay attention to, especially for some of the parts you guys may be making in class here. This is for through holes. This slide is.
Slots too.
Slots, through holes, any features that would have two open ends to it, right? So anything under 60 thousandths, we like to consider this a 2-to-1 ratio. So that's the diameter of the hole to the depth of the hole, being that it's a through hole. When it gets a little larger, you can go 3-to-1, up over 1/4 inch, or that's 300 thousandths there, you can go 4-to-1. And once you're over an inch, you really don't have to worry about it, but say a lot of these parts we are making in our industry is a lot of detail. They're trying to get rid of machining operations, so it's very beneficial to cast the hole instead of machining it later on. And now you guys can take that in class here, and if you calculate your through hole ratio, or if there's a slot that you're trying to cast, you should be able to cast that if you calculate it properly, instead of machining it later on.
So that big one there, so it's 6 inches thick, you can do 1 inch?
Yes, that's
Yeah.
a 6-to-1
You can do a
ratio if
6 to
it's
1.
over one inch.
Right. And so, tell us why you can't do, like a bigger ratio?
Surface tension is basically what it comes down to. Because if you've only got this deep of a hole to fill, the slurry should flow down in there, no problem, okay? If you're starting to get deeper, so say that hole was this deep, your slurry is only going to come down so far before it wants to stick to the walls and not flow down into the bottom any further.
Just think of that slurry as pancake batter. How far can pancake batter flow?
Right. Now you're talking about a pretty viscous liquid. It's pretty thick. It flows pretty well, but at a certain point, it wants to just grab on and stay put. It won't flow any further. This especially becomes true where it really becomes difficult is like on second and third dip, where you already have some slurry and stucco on those
It
side
gets real
walls.
narrow then, yeah.
Yeah, it gets narrower, and you're trying to flow pancake batter over gravel on the sides, so to speak. So now, not only do you have surface tension, but then you have a mechanical lock that slurry doesn't like to flow over the surface of the stucco from the previous layer.
Is there any way you could like induce pressure or vacuum to make it to get past this, or is that kind of not practical?
There are a couple different things you can do. Vacuum is one of them. Pine tree castings, it's actually owned by Ruger. The castings made for Ruger firearms. They do a vast vacuum-assisted process where they'll dip the mold in slurry, then they'll put it in like a vacuum chamber, pull a vacuum on it, and it brings a lot of air bubbles to the surface.
And it also, does it allow it to go down in deeper holes?
And deeper holes too. Yep.
Because there's a bubble in there.
There's a bubble in there. The bubble
Pulls the
wants
bubble out,
to come out.
and then the slurry goes
Slurry
back
can
in.
replace it. Exactly.
Huh, that's cool.
So.
Along those lines though, especially for if you guys are dipping fine features, you're gonna be able to achieve that with your angles of draining. So like you gotta think like that robot short video was. It's angling the mold up, so the slurry is going to come down into your fine features. It'll angle it down. You rotate it a little bit. You want to get the slurry moving around the part so it's filling in those fine details. And that's how you would help with that. Other items is you can blow a short blast of air on it.
Yep.
You're just trying to get it to slightly go into a feature, but that you'll have to be very careful with that. That's from a distance.
Right, yeah, we'll use a high pressure air blast, just a quick psst, and to pop bubbles. You can also use vibration, works fairly well, to get the slurry to kind of breaks the surface tension of the slurry and kind of lets it
You
run.
dip it and then vibrate the whole tree?
Yep.
Huh.
So that works very well, actually.
So now this is more onto the idea of if you have a blind pocket. So say you've got a blind hole, you don't want it to be completely through, and you want to tap it later on. So this helps in the machining process. We could cast the hole and just tap it immediately instead of having to drill and tap it later on. Speeds up our manufacturing. But our limitations, once again, are this is a 2-to-1 in the other orientation. So you want to be, well, that's 1-to-1 there, but
Yeah, blind holes are tougher. You typically never want to go more than 2-to-1 on a blind hole, no matter what your diameter is. I mean, within reason, obviously. But when you're in the smaller range, 1/4-inch size hole, you want to stay 1-to-1. Smaller yet, 60 thou, you want to be maybe 30 thou deep.
and that's where it's really necessary for you to get those proper drain angles when you're doing your intermediate dips.
And this is a problem we run into fairly regularly because a customer comes to you and says, you know, I want this part, I want these features. Our estimators and our project engineers say, no problem, we can make it. And then the process engineers have to dip it. So a lot of times we, Bill comes to you with a part that's got a 4 or 5-to-1 blind hole in it,
It was 3.5.
and you gotta dip it. So there are, you know, with some tricks and angles and that kind of thing, you can do a lot, but general rule of thumb is 2-to-1. Stay 2-to-1.
You know, it typically happens when someone says your maximum is this, that means, in other words, it's difficult to do that, they'll design it right to that maximum.
Oh, yeah.
Yes.
And then some.
I don't know, on purpose, or they've heard that number, so that's what they do.
Yep.
You have to tell them like a number that's half that number.
That's why we usually give this to our this seminar to our customers, and it gives them an idea of what we like to look for. This is a good example of the extremes that we cast. Those are pump, joints on the left side, 100-pound castings. On the right side, I think these are components for a screen door, aren't they?
I think so.
Yeah. Now we'll just get into a few different characteristics and whatnot. When you're thinking about more of a manufacturing sense, but you have a gate contact from the part to the sprue. In a lot of cases, that's not acceptable in the final application, so you have to design around it. The obvious is to grind it, right? Depending on part features, you may not have a flat, perfectly square face for you to just hit with the belt sander and square it off. So we have a swivel grind, and all these have fixtures that you'll put it in. A robot will engage in a belt sander, and an operator will be fine-tuning for the final gate widths. Other applications, maybe if we want to drive costs down in the part and increase speed of manufacturing, you can create a recessed pad. So on the bottom left, you'll see that was a flat face initially, and we recessed the face in, so we can leave our break-off witness without having to touch it. And it still fits in the part application, no problem. Again, in the right, maybe you're on a face that isn't critical to the customer. So in the final application, it's not a problem.
So you just don't have to take it off at all?
Right.
Just
Yeah.
leave it
Once
as
it's
is.
removed from the main sprue, the part is able to be processed through and fit in the final application. Yes.
How do you guys break it off like that?
We have a top secret process that we do, but right.
We create a stress riser at the point where we want it to break. Go back one.
Yeah.
So what we'll do, this is probably the easiest one to see. So what we'll do is actually create a stress riser right here along this plane where we'll put a notch in the gate, so that makes it the weakest point to break. And then with a little bit of assistance, we'll whack it with a hammer and it'll break off right there every time consistently.
Common industry practices are chop saw, some sort of an abrasive saw, or a, I think even
Yeah,
some
abrasive
places
cutoff
will use
saw.
like a bandsaw or
Sometimes
whatever.
bandsaw.
Usually it's an abrasive saw though. And in a lot of your situations, you're gonna rely on an abrasive saw to remove the parts. Solubles, you wanna talk about those?
Yeah, we can talk about solubles. When you got some pretty difficult internal geometry on parts, you have internal passages, ports, that sort of thing, that's not a toolable design. So when you want to build something into a wax tool, you know, you need, if you're going to have ports and passages, they need to be pretty square to where you can pull a slide out from it. If you have internally curved surfaces, we need to do something that's called solubles. So what we'll do is inject with a different type of wax what the internal passages are supposed to look like. So that's what you have right here. So that's what the internal profile looks like inside this part. So once we inject the soluble, we'll put that in another wax dye and then inject pattern wax around that soluble wax. So two different types of wax. From there we'll use a citric acid bath that'll actually leach out that soluble wax and leave you with your internal passages in your part.
So it's like a core
It's,
for creating the wax.
it's like a, yeah, it's a removable core, basically. So
Cool.
then you're left with the metal part in the end after you go through your dipping process. Sometimes some geometry is too small to use a soluble, which is a part like this. You can see you have ports here and ports here. Now those ports come all the way down and actually come out these sides. Now this is too small to be using a soluble core, so we'll actually use a ceramic core, a lot like green sand casting.
You could cast the soluble
Yeah.
core, but you couldn't get slurry down into it, right? 'Cause
Exactly.
this exceeds the rules we already learned about the depth
And
and
that's,
width.
right, once you get that small, it's going to be really hard to dip it, so that's where we'll usually use a ceramic core. So that part that's going around right now is a soluble core.
How much do the ceramic cores cost?
It all depends. These little guys, like for that, I think cost a couple bucks, $2-3.
The tooling's pretty expensive though, isn't it?
Depending on the complexity.
Depending on the complexity and the tolerance. Tolerance comes into play hugely with ceramic cores like that. And the price gets astronomically larger as your core gets bigger, because they become harder to make the bigger and bigger they get. I just ordered some prototype cores that are 1.3 inches in diameter and 22 inches long. Those were $56 a piece, with a plus or minus 10 tolerance. So I asked about a plus or minus 5 tolerance, and the price was over $200 a piece. So it goes up a lot. So in the case of the ceramic core, that core will stay in the part all the way through the casting process. So we'll inject the wax around it, build our shell around it, pour metal in it, and then after casting we break all the shell off. We'll then remove that core. Water blast will take a lot of it out, and then we'll use a caustic salt solution to dissolve the rest of the core out. Yep.
So how do you keep those cores in place after the wax is?
So yeah, you have these little nubs that stick out. That's actually part of the core. So the nubs will actually stick out beyond the end of the wax. So then the slurry you build around the wax pattern will actually grab onto that core, and it'll actually become part. It'll kind of build
So, like
around it and
creating
hold it in
some cork
place. Yeah.
Okay, so in the industry concept of these parts, we look at cost drives everything, right? So pieces per mold, and now you guys have a concept of what the mold would look like. In our facility, we like to fit as many pieces as we can on the mold, which would feasibly make sense within our parameters. The more pieces, in most cases, the more pieces you can fit on a mold, the lower your overall cost per piece. There's a lot of details that can muddy that concept, but That's a good rule of thumb. Also, the number of gate contacts you have on a sprue, and gate contacts on a part. So if you have only one, you only have to grind one gate. If you have several, now you have several operations you have to perform to this part for a gate grind. Size is a big driver, because if you have a large casting, you're putting a lot more materials into it. You have more metal you're putting in, you have more wax for the injection, you have more ceramic you're coating it with. You know, all your resources, you're putting more of them in.
It also works the opposite way too. When you get to the extreme small end of the spectrum, you know, you physically have to have your sprue, and you have some standard sizes of things, standard sprue sizes that way. So you could put a bunch of parts on a mold, but it becomes that you have way too much sprue basically for the small part that you're casting. And it comes down to somebody has to inspect that part as well. So you want to be sitting looking at tiny little parts all day, you end up going cross-eyed within a couple hours.
Yeah.
So it becomes difficult on both ends of the size window.
Other main drivers are alloy. Yeah, you know, if you want just a low carbon steel versus some sort of a rare or more of an exotic metal, I guess. Tolerances, kind of like Andy mentioned with his example of the ceramic cores, same concept applies. If a customer comes in and says they want plus or minus 5 thousandths on all their features, we're going to have to put a lot more items in place to control that. Whereas if they said, you know, plus or minus 10 thousandths on all their features, we may be able to cast it and not even have any controls in place, just because of our variation is very minimal throughout our process. And then finishing. Great example is this part in the picture. You look at it, yeah, at first glance it looks like a great investment casting. You start looking at it a little more in depth. Well, there's the striking thing right off the bat is you have bushings pressed into it. So we pressed bushings into there, but that wasn't the first thing we had to do. You think about your order of operations. This thing was cast. We removed the gate at some point. And then we had the machining operation. You can't quite see it in there, but these two diameters were actually machined to a specific size. Most likely there's some sort of bearing race that gets pressed onto there. And then we had to heat treat it to get that, that black surface finish. Either that's a heat treatment or it's a black zinc coating. And now we pressed in the bushing. So you have all these operations you perform to this part that drives your cost significantly more than if the customer said, you know, just give us a raw casting.
So just the raw casting by itself is probably maybe $7, something
Yeah.
like that, maybe.
$5, $7.
Yeah, $5 to $7. Now that we did the machining, we did the specialty heat treat, we pressed the bushings in, you're probably talking more like a $30 part.
Yeah.
Wouldn't you say?
Yep.
So,
Is that $30 what they pay to get it all done then, and they?
yeah, that would be $30.
With
They
the
receive
profit
it
margin
like
and everything.
this, yeah, with our profit margin, that sort of stuff.
So with all of this comes a lot of engineering. We do a lot of upfront design work, engineering work, planning. Nothing hits the floor without already having been designed and figured out. So just like you guys are creating your procedures and everything, you're doing the initial testing and all the identification of what's the best way to produce this project or this part. We have to do that with our projects, so then when we hand it off to our manufacturing floor, they can replicate our exact sampling process. They can do in production without any issues. If they can't do it, they're going to come to you and they're going to ask questions until we can figure it out. So the better you do up front, the easier the part is to run in production. So things we're performing right off the bat. We get a part CAD model from the customer. We're going to figure out our gating system on it. We're going to figure out where it's going to fit on a sprue, what kind of sprue. We perform solidification analysis, just like you guys should be performing to your parts in a lot of cases. If you're, you may be using Magma, but we use solid cast, so we'll do a simulation to see where is the shrink in these parts. We have many specifications from the customers that require certain levels of acceptable shrink. So we have to take our best foot forward and make sure that we're doing our due diligence to make sure there's no shrink in these castings. We always look at how can we reduce cost. So sure, we could make the part, but how can we make it the most efficiently so we are producing it for the lowest cost internally, which we share a lot of that return in cost reduction with our customer. In some cases where maybe the part is too complex for us to be comfortable with putting it through an initial testing process and putting it into production, we'll do prototyping. And that's kind of like what you guys are doing right now. You're doing prototyping to determine, is this a feasible thing to even make? We can get into prototyping in a minute, but otherwise, common processes are a new product launch. So every part goes through the initial stages I explained, as well as you get into setting up all your work instructions so another operator can go through and do exactly what you planned out initially. All of our, usually our customers will send us a CAD model, so we'll work with that before we even get our hands on an actual part. These are just some examples. I know you guys do a lot with SolidWorks. We use Unigraphics because it works good with our machining modules.
How is that different than
Unigraphics, you work on sketches in SolidCast. Everything is based, or SolidWorks. Everything is based on a sketch. Unigraphics, you can be a little more, I guess I'd call it caveman-like. You can, if you wanna add stock to a face, you can do a command called like move face, and you just click the face and you can pull it a certain distance, or if you want to subtract, you can push it away, or increase, decrease hole sizes. And now this helps out a lot when maybe the customer will give us finished machined part that's in CAD, and if we deem that that's not a castable item, we'll add the necessary machine stocks to it to make it castable, and we may have to increase thicknesses in certain areas or create feeding paths so we so we can get the proper solidification results that we're looking for. So it's kind of the same. It's for Unigraphics to SolidWorks.
pretty easy to pick up?
Yep.
No one.
Yeah, once you've done some CAD work, jumping like from SolidWorks to Unigraphics actually goes pretty smooth. It's not too bad.
So that's just a quick shot of, with all the solidification analysis we do. This is where the project engineer will get to the point of, okay, I feel like I have a steady part that I feel is castable. I'll work with the process engineer who their expertise is in making sure the solidification results are exceptional, as well as this part is going to be processable throughout the shell building process. Here's a few examples. This is one part. It's a nail gun nose for it gets bolted onto a nail gun. We tried gating this in several different locations. So you can see top left corner, these yellow spots are instances of shrink per the simulation. That was gating off the flange face. So we relocated to a little thicker mass right off the flange face. Still had instances of shrink at the extremities there. Switched it to gating at the boss, and now you can tell the orientation that the mass is above the gate. So if you envision the pouring cup being at the top of the picture, and in this view, you have your molten metal is flowing down, but you still have mass up here, so your high points have shrink in them. When you rotate the part 180 degrees, now all your mass is below your gate contact. You're allowing gravity to help you out in this case. You don't have high spots above the gate, which is your feeding path.
You're not speed uphill.
Beefier
Right.
gate too.
yeah, we've increased the gate, a little bit of redesign there, but still feeding in the same location. So these are the things, you may go through many revisions and still not have a good setup, but you have to keep going until you figure something out, right, Nick?
Yeah, only 28.
It's very rare that you hit it right out of the gate. You usually have to do a couple iterations.
Here's another example, where simulations can identify, on the left view, that's the solid model view. That may look like no big deal, it's pretty uniform wall thickness, yeah, it should solidify fine. But we determined that there is shrink in these instances. So we have some different concepts and ideas that we apply then that allow us to get rid of that shrink. That's just tweaking with the gating system and other things of that nature. So we get to prototyping, and I know you guys, some of you have printed your patterns, some are using existing patterns or are going to make actual dies to replicate it. If we get a complex shape that, maybe the customer wants it under our standard lead time, which is 8 weeks. So we don't really have any time to actually build a hard tool in that time. We can have a SLA pattern built. That could take as long as a week, quick as a couple of days, and we can process that through and have our casting. It dips just like a normal wax pattern would. We may have to tweak the burnout.
Burnout's a little tricky
Yeah.
with SLAs, but
Does that get ash in there?
it's very ashy. So what we'll actually do, remember how I said we burn out our molds at 1800 degrees? With SLAs, what we'll usually do is start burning out the mold at 1200 degrees for a couple hours. That'll burn out all the plastic that's in there. You're left with a bunch of ash, but you're still at a low enough temperature where your shell doesn't go through phase transformation, it doesn't sinter. So then you can pull it out of the oven, cool it down, and then we'll actually take the garden hose and wash out the inside of the mold to get all that ash out. Let it
You
dry.
probably have to do that, guys, if you do an FDM pattern.
Yeah, if you do really any kind of plastic type pattern, that's really the way to do it. Then you put the whole thing back in the burnout oven, go up to your 1800 degrees for 4 hours, sinter your ceramic, pour it off.
How long are you at 1200 then?
Usually about 2 hours does it. It all depends on how much plastic you really have in there. Most of the stuff that we're doing is thin wall or hollow, so usually a couple hours takes care of it. I would say definitely within 4 you should have it. Should be okay.
And burning out the SLA, it doesn't affect the permeability of that shell at all?
It doesn't, it turns into ash, and then we wash that ash out, and it turns out okay. We actually have pretty good success with SLAs.
So because of the speed that we're able to actually cast in, we can cast in as little as 4 days, 4.5 days. We can have the pattern in a week. We can run it through the casting process and call it another week, perform any dimensional checks, and have it to the customer way quicker than we would be able, and cheaper for their investment, than we would be able to build a hard tooling test, a lot of parts, a lot being, a small quantity that would fill a cluster. Disadvantages of this prototyping process is for the SLEs in specific, you're not going to obtain as close of dimensional stability as you would, or dimensional representation as you would with a wax pattern. The stability might be there, but it may not represent the variation you'll see with the wax. And any critical features, you definitely have to plan on machining those, so machining costs will be higher. In-house, we have a printer that actually prints wax, so this is very close to what we would be injecting in this case. And we can print patterns in about the same time as what you would print an SLA in. And these get melted right onto the sprue like you would a normal injected pattern, and you can process them as normal. The patterns are a little more fragile because it does have it's more like a wood grain, so they're easily breakable, whereas the injected wax is more malleable because it's our custom custom wax. This is closer to our represented overall size and dimensions. About the same time, in some cases quicker. The only limitation is size of the parts now. So we have a print sheet or a print window of 10 inches by 8 inches by 8 inches. So, you know, about a little smaller than a sheet of paper. So for smaller parts, it's great. For larger parts, then we go to SLAs. So now we'll just get into some more ideas just to get your mind going of what detail you can obtain with investment casting. I know since you don't have really any experience with investment casting, more experience with more like sand casting and whatnot, you think of, okay, you'd have to machine that intricate feature or you'd have to add that, you know, lettering later. You can put a lot of detail into your patterns and you can expect it to come out.
Pretty much anything you see in the wax pattern, you will see in metal.
Right.
Wax pattern, you grab it too hard, you put a thumbprint in it, you'll see that thumbprint in metal.
Yep.
So it makes sense that if you're making it, investment castings generally are on the more expensive side, just like lost foam. Talked about lost foam, you don't really want to think about doing it unless you have either high production runs or you just need those tolerances. So you got to eliminate a lot of machining in order to justify the extra cost of investment casting. Unless you just have someone that aesthetically things got to be polished or something like that.
Right.
Yeah.
So we'll run through these fairly quickly. This is just all examples of, for instance, you know, these are weight saver pockets. You don't really need all the mass in your metal part if you have investment casting because you can do finer, thinner features easily. And in some cases, if you're gating over here, you don't want the mass out at the end. So we want to pull the mass out of the part. It allows you to solidify better, will reduce instances of shrink. And also you think about, like these are through holes, but maybe they were beyond what our design limits are. Like we talked about through hole ratios. So we put windows in the side. So now that totally changed the game for your hole ratio. If you have a window in there, that allows your slurry and stucco to fill in, and you'll get a consistent core when you get that ceramic shell build.
When you're seeing that, okay, that hole goes all the way
Over
through
here,
it.
see this hole goes
There's
all the way
slots
through?
It's a through hole, so we put slots in there to make
This
that
is the,
typical.
yeah, like maybe the bolt head will be here and it's bolting into a feature. This isn't critical for them, it helps us, but when we
Also like
request that design, yeah, it'll request it'll lighten the overall part and
Do you sell
They're fine.
by the pound or what do you?
well, weight is a fairly large driver, but the pieces per mold is one of the biggest ones that I see at least, but
Yeah, pieces per mold is huge, and then alloy and weight of the part. You know, each, we have kind of an estimate sheet that we run through, and based on the solid model, we get a rough estimate of what the part's gonna weigh, and then multiply by dollars per pound for the alloy that's gonna be cast out of.
where weight may really come in, especially on larger parts, is you have the real estate on the sprue to fit parts, but you can't physically put more weight on because it's reaching the limitations of the process. You know, maybe the pour weight is over 100 pounds, and if we have 100-pound pouring ladles, you can't do that. So if you take weight out of the part, then you're taking weight out of overall. You can add more parts, and now you can pour more parts per mold. So it's all that larger scale manufacturing that you get into those details. But this is a good example of lettering. This is recessed in. You can also have lettering that's proud from the surface. Either one works. Proud from the surface is probably easier to cast because you don't get as the metal rushes into the cavity. In some cases you can actually clean off all your lettering and you get mold material and you don't have lettering. But positive lettering, it allows the the metal to fill into the mold. These are also some thin fins. Just adds more value to the customer, adds more detail to the part. This is a coupler with a spline. That's as cast. Oh, you can't really see it in that picture.
That's fine.
There's a spline in there. Adds value. We didn't have to broach it, whereas, you know, if this part was machined prior, they would have to broach that feature out. That's more of a clamp mechanism on a square shaft and a clevis on this end. Here's some different holes in various orientations. You know, maybe in other cases that would have had to been all machined. Well, with this process, you're able to cast all those to near that shape, what the customer needs, and if they're clearance holes for through bolts, that's not an issue for them.
Makes it real easy. A lot of times we'll cast holes and then run a tap right in. The dimensions are tight enough that we can,
Yep.
we don't even have to ream the hole before we tap.
Square holes is another example. Hexagonal holes. These are kind of an interesting case. They're the nose cone for like a drywall drill. So when the clutch ratchets on your drill for when you're running a drywall screw in, these dogs on this face are what's engaging and disengaging. It's along that slippage. So
They can wear out.
what?
They can wear out over time.
Sure.
They can, and they do. Wearing parts are good.
Right. A few other features, like this is a wrench head, and now that'll get spin welded onto a handle of some sort, probably a bar stock handle. But we're able to cast all that end feature in, so that the hole size is to shape, and we cast it in the lettering as well. This is for an aluminum shears. That's the guide plate for it. So there's no machining operations that will fit into the final assembly. These are all teeth for gears. What was this one? Some sort of a transmission component for
Internal.
hydraulics.
Yeah, internal transmission component for hydraulic transmission. That part is affectionately named R2D2.
Yeah, I kind of like that.
At the time we got that part, we were the only company that could make that part because of all the slots in the detail. That was a big one for Brown Deere 20 plus years ago.
A few more examples of, you know, racks with gears or with teeth on them.
These are all good examples of parts that would be carburized. We made out of something like an 8620, so it's tough. So you got shock loads. It's going to be tough. It can take that, but then you still want high wear resistance on the teeth. So we would carburize that.
Cases of sprockets.
So you can just use those sprockets as cast.
Yep.
Oh yeah.
Yep.
We make a lot.
The
of
sprockets
stuff
aren't
like
a
that.
big deal. The gears are more of a. That's more of something that's a little intricate. Because if you get small positives, then you're not
Yeah,
engaging.
you want positive.
The sprocket, because of the feature, you know, the chain that would ride in there, that's not a
You
huge
can ride
deal.
up a little bit at a time.
Right.
Right.
This one in the top right should look pretty familiar. Needle nose pliers. Yeah, we could pass some of these parts around too, I suppose.
true.
That little pocket there on the right, that triangular pocket, so you can put carbide in there, right?
That's a military issue version. Carbide insert goes in. Another instance of internal spline bores for couplers. Some more couplers. That's on the top right. That's a shift lever for motorcycle.
Those are as cast, or do they?
Yes, those are as cast. We also have some that are more fine that we will broach, but many of them we can cast. In the bottom right, that's a ratchet head. We do a lot of ratchets, 3/4 drive, 3/8 drive. I have a 1-inch drive ratchet head that's about yay big right now. It's huge. No, for the larger ones, they'll spin weld them right onto the handle. For the smaller ones, like 1/4 drive, right now I have a 1/4 drive ratchet project that it's the entire ratchet assembly. So they'll do the finished machining operation to the gearbox on it, and they'll insert the guts and do a polish, a chrome, and then they assemble it. blinds. These are kind of an interesting one. These are they're called mop blocks or Caterpillar. What they do is they have wear plates and they're like mining dump trucks and large shovels where there's wear pads of ductile iron or some sort of a highly wear resistant iron plate, and this lock goes into a center window, so that plate will sit on there, and they have a patented process where this casting has to compress and then spring back to clip into that feature, which retains that big wear plate on it. So it's not it's not a duty cycle spring like you'd expect a spring rate out of, but it does have to have some sort of spring characteristics. A few other instances, like you see little pegs where you'd hook a spring onto, or a lever or whatnot. This is all a castable feature. So that whole head there. This one is kind of interesting. Andy was saying this is for turning your rear brake the piston in for the rear brake caliper. Some of those you have to actually turn it. This tool is all as cast. It has those windows that are for 3/8 drive ratchet to engage into, and all the pegs are different sizes for different manufacturers. So, and that's all an as cast option. On the top view, that's I think that what was that, Mod 1? Mod
Yeah,
2?
this is one of the big parts for Mod 1 when it first opened. It's for Milwaukee Electric Tool.
The drill.
Yeah, it's
Right.
a drill bit.
It's a hole saw bit. Before they designed the whole hole saw, like the modular system where you have the sheet metal hole saw, that's an all as cast. They sharpened the edge and all the different sizes, so we have various sizes produced.
How big is that?
And
That one I think,
3/4.
yeah, 3/4 to an inch, roughly. That shank's about a half an inch in diameter, so.
What kind of heat treating would you do to the head of that?
That would be a carburized also. Yeah. That would probably be something like a 4140 and then carburized on the head.
In that instance, you wanted to have a wear resistant and abrasion resistant outer shell, but if you hit like a torque load on it, you don't want it to be so brittle on the core that it just shears. So if you have a ductile core, then it's able to take that impact. Bottom is just an inspection port. That's a cover that would go on like a transmission case or some kind of gearbox. Just different gussets. We use these gussets to strengthen as well as help feeding paths. So kind of trying to get all your thoughts going for helping your parts fill out better and increasing the structural integrity of them. A few other features with slots. If you have long holes or long ribbed areas, maybe you want to add some slots to it, which would help with getting more shell in the area, strengthening your shell. One major thing we're able to do is as cast threads. So
There's a couple of parts coming around that have as cast threads.
we're not talking just like Acme thread that's gigantic. We can do 1/4 as cast. You run a nut on it.
Put a nut on it, right?
Yeah.
As blasted.
Yep.
Now, when you make those waxes, that feature that creates those threads, is that screw off?
No.
No, a lot of times we'll do it with your part laying down this way and then we part it horizontally.
And then the flash on there, does that have to get trimmed?
Non-existent usually.
If-
Usually when it starts getting high, that's when we'll take the tool down, and usually there's a wearing item at that point that's starting to wear, so you're gonna get a little mismatch. But ideally there should be no flash at all.
One thing that we do to alleviate that issue is where the parting lines would be, we have flats on the thread. So you have
Yeah.
mostly engagement right there. It would be a flat shut off. So you don't have to worry about mismatch, and your nut will still engage, no problem.
Still got most of the thread there.
Yeah. And a lot of these cases, they're not torquing to yield, or it's not a critical application. It's just something that is driving cost, it may be holding on some small feature. Different cams, different profiles that we're trying to obtain. Kind of a dish detents we're able to do as well. Different groove features.
So like cam grooves, right?
Right. Now, certain features may be, they may be dimensionally concerning. If you have two arms out there, they could move back and forth when they're solidifying.
Where are the part that we're making those oarlocks have a tie bar on them.
Okay. Yeah, so a tie bar will help the dimensional stability. You'll want to put it out at the very end, which will hold everything together throughout the wax, throughout the shell building, and even in casting. Otherwise, you can get a bow to it or some kind of feature that you'd have to straighten later.
This is like a wire harness?
That's a fall protection piece that'll go onto a cable.
Oh, okay.
Like there's probably one in the safety lab next door. It's for DBI solid. They do a lot of different fall protection equipment.
Or is this like a machine one versus the...
What is? Yeah.
Yeah, the one is machined.
Yeah, we'll get to that shortly. A lot of those cases are lettering, like we touched earlier. Like you'll see lettering on a lot of cast surfaces. That's all as cast in investment casting. Date codes help you identify manufacturing senses, tracks down when the part was produced. This is where we'll get to more of a case-by-case of ways we've helped convert other processes to investment casting. In this case, this is a weldment. Some of you may recognize this. It's a steering head for a motorcycle. In their initial manufacturing process, it was 17-piece weldment. So they had all these loose parts fit into a fixture, highly time-consuming, a lot of variation. We're able to cast it. We helped them out, decreased weight. We also increased their cost savings over 50%.
And they get a much more consistent part.
Right. This is a good one. With internal passages, this is a component for an EGR system on a vehicle. Now, they may have had to machine that out of a billet before, or a solid block of some nature, and now they're able to get the as-cast shape, reduces weight, reduces cost. We just have to do some finished machining operations for the threaded fitting ends, and it's ready to go into the final application.
So they wanted that in stainless?
Yes.
Yeah, it's 300 series stainless.
This is the part that we're passing around right now. They had machined all those components from solid. We were able to cast all the features. They had less assembly to get it to the final state. The part not only is more consistent, it's also, it's not only cheaper, it's consistent, and it looks a lot better.
Plus, it's those sharp edges on there. I wouldn't want to handle that all day long.
Right. Yep. Forgings, maybe some of you have seen forgings before. This is kind of an interesting one. It's a magazine opening in a rifle. So the component on the back left kind of area, that's what a forging would look like, and they had to do all these hours of machine operation in order to get it to the finished shape. Well, we're able to provide a finished component to them that they can maybe they have to drill a few holes, or maybe they can put it right into the final application.
And actually, the newest revision of that part has the holes cast right in it. We send it to them. I think they paint it and bolt it in the rifle.
Yeah.
So very little finish work to the part before they can use it.
Another instance, this is a dollar exchanger on like a soda machine. The plastic part was getting beaten up with baseball bats. They're getting their money stolen, so the request was that we build a more durable design. We built it in stainless, and we had it wrinkle painted, so it looked like a plastic component, but very durable, highly resistant baseball bats.
Pain in the ass and gas.
Yeah. This was one where it was a machined assembly. We were able to cast the entire feature, and that's a 50% savings to those guys, and the lead time is a lot quicker. This is an assembly. So before they had, 5 pieces to their overall final component. We were able to cast the thing without even a gate grind operation. You can see we used a recessed pad. Pulled a lot of costs out of it for them. And it's a consistent piece now. They don't have to have an operator assembling all that in the final stages. So, kind of wrapping everything up, we threw a lot of information at you. So we overviewed investment casting, SigniCast itself. We overviewed the process of investment casting. We got through some very lightly touched on dimensional and geometrical shapes of the parts. GD&T, I wouldn't even say we hardly even scratched on it, but some capabilities of investment casting. Hopefully got your gears turning a little bit for what you guys can do with your project. Add some more feature, try different things, don't just make a block, Nick.
Yeah, you're gonna get a pretty crappy grade if you could have made that in sand.
Yeah, Nick.
You're gonna use the process to its fullest.
Okay, I don't know if we have enough time, but I want to hear a couple people, what's some takeaways from this? What did you find interesting? Something you're going to apply to your project, something that kind of you didn't know about investment casting. Go ahead.
I didn't know that you could get such tight tolerances. Like
Okay.
you could, like what you guys do, what you were saying about the tapping the holes, you cast it and you can tap it right away.
Right.
That's pretty cool.
And then you could cast the knurling right onto it.
Guess what?
The knurling onto that last part.
Yeah. There's a lot of detail you can add that you wouldn't know otherwise. Go ahead.
Yeah, and like you said about just if you touch the wax too hard and leave a thumbprint, you see that in the casting. I had no idea that it was that detailed.
Yep, you can pick up that higher resolution. Just, like your thumbprint, you look at that and go, wow, there's really not much there, but you will see that in a metal casting if you put it in the wax.
Yeah, when you guys are working with your wax patterns or whatever your initial pattern is, make sure that thing looks exactly how you want it to look in metal, because it will turn out that way.
There's little leeway as far as that goes. Whatever you see in wax, you will see in metal.
Just to give you a quick example, when I did this class, I made a little model truck. It had all this detail, like the trim work on the side you'd see on there. And it was a small, very small model, about that big. The air cleaner on the engine turned out, the valve covers, you could see the ribs in them, you could see the ribbing down the side of the truck. All that stuff turned out. You could see the little bolt, provisions on the bed of the thing. So, don't make a big block part, add some cool feature, like on your shifter lever. Try to add get some texture to it. It'll help with your shell, it'll help with the final detail, a lot of different things. So, don't play it cautious. Someone else.
I like the, when you're talking about tolerances, the holes and slots, the ratios for those.
Yeah.
That's some real good information to take away to keep in the back of your mind, because if you don't think of that stuff, you'll find it again once you're trying to dip that mold, and it's way easier to think of it ahead of time. Plan ahead.
You can think you have that thing filled up, but it could just be covering the hole, and there's not going to be a hole there. Or it can have a bubble in it and it breaks off.
Yep.
Yeah, and for reference, when you guys are making your project, the first, 2 dips are very essential. That's where it's going to fill in all the detail on your part. You want to make sure they're very uniform shell build. You get a good sand, stucco coating on it. Those are the most essential. That's the main integrity of your mold. The rest of it is building overall strength, so you don't get a defect such as like buckle on a flat surface or something like that. So really pay attention to your first couple of dips. Go ahead.
I don't know anything about cores for investment casting.
Okay.
Soluble cores and even ceramic cores, how they stay in the shell.
Yeah.
In the final casting.
And
How do you get those cores out?
which ones?
The soluble, not the soluble, but the
So ceramic cores.
ceramic cores, yeah.
Some of it, depending on the geometry in that and how big they are, some we can get out with just water blast. If we can't get it out with water blast, we use a caustic salt solution to dissolve the ceramic.
So they actually put it in a
It's
tank and
it's a
dissolve it out.
molten salt bath.
And that doesn't affect the metal at all?
Doesn't touch the casting, leaves you with a little bit of a rusty surface. But as long as you're in and out fairly quick, only use as much as you need, it won't touch the casting. Over time, you leave casting in the caustic solution, it will eventually corrode away, but we're only in for a couple hours, and that won't happen.
Somebody else? Takeaways? Something you're gonna add to your project now that you've seen this?
When you do the wax, is that kind of like injection molded process for that?
It's just like plastic injection molding,
Okay.
except we're injecting wax instead of plastic. And actually, our plastic feels almost more like or our wax feels more like a plastic than a wax, like you would normally think of it.
Alright. I was just wondering if that was like gravity, you melted it to liquid and then just poured it in the gravity or...
No, it's a pressure injection.
Alright.
Usually we're injecting somewhere around 800 to 1200 psi.
How much do the molds for those, parts cost? You're saying they're 75 aluminum, but like obviously.
Oh, and actually, the die itself?
Yeah, yeah.
All depends. Usually they're in like the $20,000 range. It's pretty fair. We have some more complicated ones. One in particular was about $47,000.
Yeah. That's for the very complex ones.
For the most dead simple, just manual tool, where a guy would, open it up, you're looking at $2,500 to $5,000.
Yeah.
Yep.
I had a question on, as far as the cores, so does that almost requires you to do completely, to do the manual, I don't know what I'm trying to say.
Oh, like, yeah, a manual process?
Manual process, yeah.
Yes, when you do a core, you physically have a person standing there at the press, and there's actually, the cells that we have set up for our soluble area has two presses, one here and then 190 degrees. So they'll be making soluble cores on one side, injecting the cores themselves, and then they'll take those cores, move them over, set them in a pattern wax die, and wrap them with pattern wax right then and there. So one person is operating two presses.
Does that limit your productivity on those kind of parts then? Like, do you have a certain maximum capacity you can do with those kind of parts?
Yes and no. We have enough capacity kind of built in that we've never really hit the limit, but they are considerably slower running than a regular, typical wax pattern.
The way we capture I think you're referencing to like the rate at which we can assemble them and get the process going.
Yep.
That's all captured in our cost. All the lead times and everything, we have a scheduler that he's setting up and coordinating all the jobs to run through based on the customer's need. So if we have calculated down to the day of how long a process will take. So if it's 8 days to when we have to ship, they're going to make sure we get going, a day to 2 days ahead of time if we can, to make sure the plants run smoothly. We don't want to stack up a bunch of slow jobs at the same time. So that's something in the manufacturing stance that you have to make sure you're watching that sort of thing. Go ahead.
So,
When you like melt the wax out, the process, it takes like 3 seconds or whatever with the steam. Is there other processes that you can use to get the wax out instead of?
There is, some companies will take that mold with the wax in it and flash fire it. They'll put it right in a burnout oven.
Okay.
That's kind of what we're doing.
Yeah, that's kind of what you guys are doing. Tends not to work as well because that wax wants to expand. And if you don't have the pressure of the autoclave holding it back, a lot of times your mold is going to crack. People have dabbled in other ways to de-wax. Instead of an autoclave, they've tried just shooting steam up the bottom of the sprue to melt the wax out. That actually works surprisingly well. Better than
Like a
you would.
hollow sprue or
Nope, solid wax sprue.
just a high pressure, high temperature steam?
High pressure steam, just shoot it up there and it starts at the bottom and starts working its way down and it ends up pretty much de-waxing the whole thing. The problem is that takes quite a bit longer than an autoclave cycle. Normal autoclave cycle is like 15 or 20 minutes. It takes about an hour to de-wax a mold, shooting steam up the sprue.
The ring of fire takes about 5 minutes,
Okay.
but you have a much higher percentage chance of
Of cracking.
breaking the shell.
Yeah.
How do you stop the shell from cracking?
That's where the pressure in the autoclave comes in.
Well, like for us, we don't have.
Build a beefy shell.
Yeah,
There's
more
no-
layers, more layers.
Yep, that's pretty much all you can do. You can kind of help yourself out if you're gonna try and de-wax from the inside out, like with steam or with a torch or something like that, by cooling down, keeping your shell itself cool, and try to melt from the inside out. That'll help somewhat. Depending on the wax you're using, microwave works. Where a microwave, depends on the wax, obviously. Like a normal paraffin wax, it won't work, but a lot of the fillers that we use will actually get hot by using microwaves. So you can literally put a mold in the microwave and melt the wax out.
Yeah, our microwave pro. We had one of those, we could do that with. Actually, the best microwaves are the super old ones. Pick them up on you find one that's actually still working. Sometimes people just replace them because they don't like how they look. Industrial one. You can also put coolers on the elements on those things. You can put water cooling on the elements, so you can actually melt metal and stuff in a microwave.
That's that one microwave AFS has.
Yeah, those little, they actually, you're heating the crucible, not the
Oh.
metal. It's got receptors and it's. Well, we want to take a break here, and then maybe can we talk a little bit about refractory.
Slurry testing and that sort of stuff?
Yeah, how to maintain the bath and everything.
Yeah, we can do that.
Okay,
Did
let's
you-
take a little break, guys.
Did you check and see if you still have the recipe?
What's that?
Recipe? Did you check on that?
Oh, so will they have it? I'm logged in there, I'll take a look.
Oh.
I was in for some.
For that,
Yeah.
Right?
I think you had, it's kind of.
Do you want these?